But okay, so chapter 7 is about rotational motion and gravitation. Okay, we basically in this chapter we kind of start a new motion, but we're going to repeat our cycle of this logic here. We start from kinematics and we go dynamics, and then we do advanced concepts. In chapter 7, we start from kinematics and we'll do a little bit of dynamics. Okay, and in chapter 6 we'll do in chapter 8 we'll do a little bit more dynamics. But I don't think we will get to angular momentum in chapter 8. We don't have that much time. So we start from introducing the kinematic quantities. There we very analogous to what we did in chapter 2. We had angle instead of position, angular displacement instead of displacement, angular velocity versus velocity, angular acceleration versus acceleration. So we got, and then we introduced this new unit called radian. It's defined as arc length divided by the radius, okay, for the angle, okay. And then we have the corresponding, these 2 units. And then we got all these other things, theta, omega, alpha, et cetera, et cetera. So and then we talk about the 2 specific kind of rotations. And we start from constant angular velocity motion. That's really simple motion. We also sometimes call it uniform circular motion. And the most important one for us is constant angular acceleration motion, which is analogous to constant acceleration motion in chapter 2. Again, the formulas are very similar to each other. If you replace the corresponding quantities, v to omega, a to alpha, x to theta, you got your new formulas. And then we did one example for that, okay, for that motion, okay. And then we did a relation between linear and angular quantities by using this definition of angle in radian. We were able to get the relation between angular speed and linear speed. Notice these are only the relation between the magnitudes, not for directions, okay? But in terms of magnitude, omega will be over r, okay? And then we got the angular relation between the angular acceleration and the tangential acceleration, which we didn't emphasize a lot. The most important thing for us is still this one, v equal to omega r, or omega to v over r, okay? Well, that gives us a very interesting thing that when you have a continuous mass rotating, the different locations have different linear velocity, even if they have the same angular velocity, because the linear velocity depends on the radius. And we use that to do the exercise for calculate the angular speed and linear speed of the Earth, on the Earth. At different positions on the Earth, the linear speed will be different, although the angular speed are going to be the same, okay? So that's what we finished last week. So this week, we'll move on to the next subject, which is basically a little bit dynamics, okay? We don't talk about forces, okay? So this is item number 4 for this chapter, okay? Okay, hold on, okay. Now, before I write down title for this item, let me ask you this question, okay? Let's consider a simple rotation, the simplest possible rotation, which is an object rotating on the circle and with a constant angular velocity. So it's a uniform circular motion, okay? So basically omega is constant, okay? And because v equals to omega times r, the linear speed is also constant, okay? Speed is constant, okay? Now I have a question for you guys, okay? Do you think in this case, okay, when the object doing this uniform circular motion, do you think there's an acceleration on the object? Is there an acceleration? Okay, let me. Acceleration. Okay, send me a message. Tell me what do you think. Okay, I got 1 answer. Okay, 2 answer. 3 answer. Okay, wow. Okay, I got 4 people saying, 3 people saying yes, and 2 people saying no. Okay, oh, 3 people saying no. Okay. Now I understand that for people who saying no, that because you probably feel like the speed is constant, right? So there shouldn't be acceleration. So now what about people who saying yes? Why there is an acceleration? Where does the acceleration come from?
The direction is changing all the time.
Okay, yeah, good point. Okay, remember, okay, here is a very important point. Remember, acceleration is a vector, right? So our definition, A equal to delta V over delta T, okay? Well, this V here is also a vector. So even though the speed does not change, the magnitude stays the same, but the direction is changing. So if you draw 2 velocity vectors kind of close to each other, one here, let's say, okay? So see, they have the same lengths because the speed are the constant, but they have different directions. So you call this VI, you call this VF. And delta V, okay, equal to VI over VF, but it's not 0, okay? Remember, vector, this is a vector subtraction, right? One vector subtract another vector. If you draw them like how do we do that, right? What we did was we do it like a vector addition. So we draw we draw VF here, and then we draw negative VI. So VI goes this direction, negative VI goes this direction, right? So this is your VF, this is your negative VI. Okay, so then we add them together. So here it's going to be our VF minus VI. Okay, so as you see here, this vector is not 0. So that means delta V is not 0. That means A is not 0. Okay, so there is a acceleration here. Okay, now which direction does the acceleration go? As you can see here, it's more or less go towards the center. See, remember this is kind of like your circle. So if you draw VVI here, negative VI is here, right? So this one goes toward the center. Actually, turns out we can prove it goes there exactly toward the center. Well, if you're considering 2 velocities closer and closer to each other, you know, like right next to each other, the velocity change is going to point directly, like say one here, and then it's going to point exactly to the center. So delta V is going to be toward the center, and then 0 for A is going to be toward the center. So this is a very important acceleration for us. We call it a centripetal acceleration. Okay. The word centripetal comes in because this acceleration point toward the center. Okay. And we use C to label it. So AC, we normally call it AC. C stands for centripetal. Okay. So what we see here is even for the simplest possible rotation, when the angular speed is constant, there's still a linear acceleration associated with it. The reason for that is simply the velocity is changing direction all the time. In order to change the direction of velocity, you need an acceleration. Okay, and this acceleration point toward the center. So if you draw this circle here, and anywhere on the circle, if you draw the acceleration, it's going to be like this. Okay. Again, I emphasize it is very important. Okay, it is critical to know that there is acceleration and it goes towards the center of the. I mean, again, it exists for all rotations. As far as you're rotating, there is a centripetal accelerated motion because the linear velocity changes direction. Okay, all the time. So you need an acceleration to do that. Okay. Well, this is the part of the dynamics we want to talk about. Okay. Because of their acceleration, according to Newton's law, if you have an acceleration, there must be some forces, okay, to back you up, to support you, okay, and that is actually the message here. I mean, the dynamics we want to talk about. Okay, so first of all, let's try to figure out give a formula for the centripetal acceleration. Okay, so what is the value of the acceleration? So again, I have to kind of do a little bit rough, you know, a little bit hand waving. Because to do it rigorously, we need a little bit of calculus, and it's kind of going above the scope of this class. So again, consider the two nearby velocity here. One is like this, the other one is like this, you know, VF and VI. Okay, so in order to get the acceleration, we need to get the velocity change, the magnitude of the velocity change, right? As we said, if you draw them like next to each other, like VF and VI like this, I'm not drawing very well. Well, this gives the difference, you know. Is that right? Yes. This is a delta V here we have, okay? So how to calculate this length here, okay? Well, you can actually recognize there are two similarity angles. One is this one with delta theta, which is where the rotation goes, how much is rotated. Well, that is actually similar here. It's also delta theta here. So basically, we could say that delta V, the magnitude, okay, equals to this arc length, which is V here, times the angle theta, delta theta, okay. Okay, sorry, I'm sorry. This is not arc length. So roughly, this is the arc length, this is the radius, this is delta theta. So it's kind of similar to this one. So delta V equal to V times delta theta, okay. So what does that tell us? Okay, if we divide on both sides by delta T here, so we'll get this part here is nothing but our centripetal acceleration, AC, because that's the change of velocity divided by change of time. Well, what do we have on the right-hand side? Okay, we just write here like V. That's the speed of this motion, and delta theta over delta T is just the angular velocity. So AC equal to V times omega. Okay, and because omega equals V over R, right? Because the relation we just talked about last week. See this one here, this one. If you plug in here, you have V squared over R, okay? And that's going to be the formula for our centripetal acceleration. So let me write it here. AC equals to V squared over R, okay? And that is, the critical formula we need, okay? That means if you have something rotating with a linear speed V, you need a centripetal acceleration V squared over R to keep it rotating like that, okay? To keep changing the direction of the motion, okay? And that is critical. Without that acceleration, you won't be able to rotate, okay? So with that, we could actually now talk about our dynamics with Newton's law, okay? Well, in those dynamics cases, we focus on this specific acceleration, okay? So maybe before that, let me explain another thing, okay? So for a motion in general, I mean, a general rotation, like say an object on the circle, in general, there could be more than just centripetal acceleration. There could be, see, there's an AC here, as we know, there's always, but there could also be another acceleration going along this direction. This is what we call AT, okay, the tangential acceleration, okay? Well, each one of them has a different role here. AC, as we know, the role of AC is to change the direction motion, like we talked about. Well, another AT here is needed if you have a change of the magnitude of your velocity. So the magnitude itself is changing. In that case, because magnitude change, so you have, it's not a constant angular velocity motion. It's actually angular, it could be angular, constant angular acceleration motion. So but this two acceleration has different roles here, okay? So in general, you could have both of them, okay? Well, this might be a little bit confusing for you, but there's always these two accelerations, but they are always perpendicular to each other. So these two directions are totally independent of each other, okay? Like as the object rotates. And in this class, mostly we focus on this one here. This one we can talk about, but it's a little more complicated. And actually in chapter 8, we have time, we could talk about this one, but we probably don't. So let's just focus on this one, okay? Again, this one is always there. As far as you're rotating, you need a centripetal acceleration. Well, we may or may not need the other one, okay? Do we have any questions or we're good? Okay. So, okay, now let's do dynamics. You guys can see this YouTube video, right? Let's see this, okay? So this is like so-called motorcycles in the cage. I don't even know there are better name for that, but look at these guys. Okay, they're going like rotating around the cage. How many of you have seen this before? Okay, yeah, like you go to like circus or state fair, you know, these kind of things. You can see this. So one thing you notice crazily is these guys do not fall off the cage, right? Let's say even they're in a crazy situation. Like, I mean, I guess we can. No. I mean, maybe let me go back here. See, right here, right? They're going totally upside down on the top of the cage, right? But they never fall off the cage. And certainly they're doing rotation. So there's something we can figure out based on what we learned. So let me go back to our whiteboard. Okay. So here's a question we want to address. So let's draw this cage here. Okay, say this is the cage. Now we have this guy riding a motorcycle here. Okay, and totally upside down, like this. The question is, why doesn't the bike fall off? What do you guys think? It certainly does not fall off, right? As you see here, right? Now let's do free body diagram. Let's draw forces. What kind of force does this whole thing have along vertical direction? Well, certainly there's a gravity. It's going down. There's also contact, right, from the surface. That means there could be a normal force. But if that's the case, the normal force is also going down because normal force is perpendicular to the surface is going away from the surface. So there might be these two forces, but both of them going down. There's no force going up, right? Are there? I don't think so, right? There's no force going up. So we see there are two forces going down, but why doesn't the bike fall off? Does that violate Newton's second law? Okay, try to answer it, maybe either talk or send me a message, you know. It's an interesting question, right? I mean, it's a fascinating question to think about, you know. So when you learn something like physics, you should try to connect it with your everyday life, you know, to see whether you can use physics to explain something you have every day, you know. And sometimes it's especially fascinating if you see there are cases you feel like it does not apply. Well, there's definitely something in there, right? Because if this thing does not apply, that means there must be something wrong with Newton's law, you know, or it might be you missing something in your analysis, you know. And this kind of question is always interesting to think about, you know. And anybody? Okay, I got a message here. Let's see. Okay, there's somebody saying the velocity. Well, that's definitely true. Okay, it is definitely the velocity that's doing something here. Okay, but that's not exactly it doesn't explain the whole story. Because the rotational force equal to two force going down. Okay, well, that's a way to say it. I mean, there's not a person saying that. But what is the rotational force? Have we ever talked about any force called a rotational force? We don't, right? We've never talked about that, right? So there's no any other forces beside these two forces. Okay, you may heard about something like rotational force or centrifugal force or something, but they are not real forces. Okay, I do not want to use them because they're gonna only confuse you guys. Okay, we only focus on real forces as we explained so far, and there's no real force called rotational force. Okay, well, certainly the velocity plays a role here. Okay, because we never see anything that's like a motorcycle stopping here and then it still stay there, right? It never happens, right? I bet you've never seen that. I never seen that as well. It seems like the velocity is the key. And you have a feeling that these guys have to move relatively fast in order to stay on the cage. If they move really slow, you have a feeling that they will fall off. And actually it's the case, okay? You have a feeling, you have intuition that the faster they're moving, the safer they are on the top of the cage, which is actually the case. All of these, I mean, kind of good with your intuition, but why exactly that's the case, right? So that's our question. So we have 10 minutes left. So let me spend the last 10 minutes to kind of explain this thing, and we'll continue tomorrow. And it's actually one important subject for this chapter to learn, for us to learn, okay? Very interesting piece of dynamics for us to learn, okay? So let's, what do we do here? We're gonna use Newton's law, okay? Let's try to write down Newton's law specifically and see whether it still applies here. So, and for our purpose, we only consider this direction. Let's define this as our positive direction, okay? Why? There might be some force along the x direction, but we don't care, okay? Let's focus on the y direction, okay? Let's write Newton's law along the y direction, okay? Now we have two forces here, mg and n. And that equal to mass times acceleration. What is the acceleration along this direction? Do we know it? Do we have any acceleration along the vertical direction? No? We just learned it, right? There's acceleration, we AC. That's our centripetal acceleration, right? Remember, there's always acceleration point toward the center. So in this case, we have the total force equal to mass times acceleration. Okay, we can write here as v squared over r. And this as mg plus n. Okay, as you can see here, right, I list from this equation point of view, it seems like there's nothing wrong. We can definitely satisfy this equation, right? It seems like there's nothing wrong. However, there is a limit here. The limit is this, okay? See, this term here depends on the speed, right? If this term has, if the speed is 0, well, you have 0 on the right-hand side. Well, on the left-hand side, you have some positive forces. Well, certainly the equation cannot hold. So that means in order for this equation to be correct, we need to have some velocity here. We need to have some speed. Okay, that's our intuition. We feel like this guy has to move with certain speed. Okay. Well, what we can calculate is so-called the minimum speed. Okay, minimum speed needed. Okay. So what is that minimum speed? Okay. That means the minimum, the smallest number for v that this equation can be satisfied. So what is the smallest number? Well, if you look at the left-hand side, we have two forces possible here. We have gravity and we have normal force. Well, there's nothing we can do about gravity. Gravity is always there. It's constant. It's always there. But the normal force here is a little bit flexible. The normal force really depend on what you need for this case. Well, for the minimum speed, that basically means the normal force goes 0. So there's no normal force. There's only gravity. So mg equals to mv squared over r. So m cancels out. So the speed is given by g times r and then square root. Now for a cage, like what we saw here, right? When the person is standing up, like roughly here, it's like half of the radius. So roughly we could say, let's take r equals to 5 meters. So the radius of the cage is about 5 meters. It might be 4, it might be 4.5, but roughly it's about 5. So we put r equal to 5 meters in there. We can give an estimate about the speed, the minimum speed. It's going to be 9.8 meters per second square times 5 meters. So that gives us 49 and square root, okay. That's 7 meters per second, okay. So if we have a specific cage that has 5 meter radius, the minimum speed we got is 7 meters per second, okay. So that's roughly 15 miles per hour, okay. Close to that, okay. So that number is not a big number, right? You can easily achieve that number by riding a motorcycle, right? 15 miles per hour is not much for a motorcycle. Some people can even do it with a bicycle. Okay, you can ride a bicycle, get to this 15 miles per hour. Well, some of the videos you can watch on YouTube probably give you like bicycle inside of a cage. You know, the bicycle you can ride a bicycle, go upside down. You ride it really fast, you can do it. Okay, it's more difficult to do than the motorcycle, and it's more dangerous because if you lose your power, you know, you start paddling it, you may fall off the cage. Well, which is dangerous. Well, you rarely see anybody running on the cage and going upside down, because that's even harder, you know, to go like 15 mile per hour running is not easy. Okay, I don't think that's easy. Okay, so anyway, so even like, see, okay, I guess you can be like 7 meters per second, right? If for 100 meter, that's gonna take about 14 seconds. So definitely people who do like race, they can do that 7 meters per second. Okay, they can do it, but not for a really long time. So it's still very dangerous. I guess some people can do this for us. Maybe try Google some videos like YouTube or something. See whether you can see somebody running inside the cage or something. Okay. Anyway, what we say here is like as far as the person is going velocity larger than the minimum velocity, we're good. Okay. As far as v larger than gr, we're good. We're good meaning that Newton's law can be satisfied. Okay. Well, in that case, if v is larger, we just need to have some non-zero normal force. We have larger and larger normal force to kind of compensate this large velocity here. Okay. But in any case, we don't see that this thing falls off as far as v is larger than that. Okay. Now, why is that? Does that well, we have total net force going down, but why can't we stay there? Why can't we just stay there instead of falling off? Okay. Well, this actually goes back to the original question. Why do we think something has to fall off if it has a net force going down? Okay. Well, it turns out it's not necessary. Okay. It turns out that we could have something with net force going down, but not falling off. Okay. Because in that case, see the case we have here, we have net force going down, but that net force just provide us a centripetal acceleration that's pointing towards center so that the direction velocity can be changed. So instead of falling down, instead of giving us a linear acceleration going downward, it gives us a centripetal acceleration that keep this thing rotating, okay? So to have a net force going down doesn't mean that you have to have a motion going down. So you could have a force going down, but not a motion going down, okay? In our case, we actually have a velocity going this direction, okay? So if we have a velocity going this direction and we have a force going this direction, perpendicular, what this force does in our case is it provides us a centripetal acceleration that changes the direction velocity. So the thing going on the circle, but it does not fall off. Well, we do have some cases that this thing could fall off if there's no velocity. If the velocity is 0 here, there's a force going down, this thing going to fall off, okay? Well, that's our free fall, right? Well, in this case, instead of doing free fall, it's doing circular motion. And actually, we've seen another case already before. Remember, we have this projectile motion. Okay, this is let me draw a circle here. Well, in the case of projectile motion, when this thing in the air, there's still a force going down, right? This is gravity, but that doesn't mean this ball is going to go like this, because there's going to be always a velocity going like a horizontal direction. So instead of falling down, it's doing a projectile motion. So as you see here, to have a force going down doesn't necessarily mean that you have a motion going down. You could have all different kind of motions depending on your velocity, okay, at the moment. So our initial question was not right in the sense that we thought whenever we have a force going down, the motion has to go down. It's not like that, okay? We could have all kind of different cases depending on the velocity, okay? Did that make sense to you guys? Okay. It turns out what we learned today is a very important piece of physics. Tomorrow, I'm going to explain this piece of physics is actually very important, not only for making sure the motorcycle does not fall off the cage, but also making sure our whole universe is stable. And make sure that we live in a galaxy that stable by itself, okay? It's a very important piece of physics for astronomy, for cosmology, okay? So I guess too much for today. So let's stop right here. And today we'll talk about some application for astronomy as well, okay? And which is also very, very useful for us, okay? So let me kind of, as I mentioned toward the end of last class, this piece of physics we just learned is very critical, okay? Not only for making sure that somebody riding a motorcycle in a cage doesn't fall off the cage on top, but also it's very important for the stability of our universe. Okay, so for example, let's think about this question here. Okay, so we know we have the Earth, right? The Earth is here. We know there's a satellite of the Earth, which is the moon, right? We know the moon is rotating around the Earth. Okay, I'm not drawing very well, but so here's my question: how many forces do we have on the moon? If you just consider this two-body system, what force do we have on the moon? I mean, you can send me a message. What kind of force do we have? If you can just consider these two objects here, the Earth and the moon. So what kind of force do we have on the moon? No. Okay. First of all, there's no normal force. Okay, remember normal force, you need to have a surface. There's no surface, it's space, right? There's no normal force. And second of all, AC, that's not a force. Okay, it's an acceleration. So yeah, because they're doing circular motion, it has to have a centripetal acceleration. That is correct, but that's not a force. Well, it turns out the only force you have on the moon is gravitational attraction, or you can call it gravity, from the Earth. Okay, so the Earth provided gravitational attraction to the moon. And that one, we learned from the chapter 4, it had this formula. This is the magnitude, and it is a attraction. It's universal gravitational attraction. It happens to any objects, you know. Okay, but here again, you can ask a similar question. If this is the only force on the moon, right? It's pulling it towards the Earth. How come the moon does not hit us? Does not go collapse with the Earth, but staying in this rotation? Well, the answer is the same as in the case of the motorcycle in the cage. Okay, because if you do the set up Newton's law here, you have a force which is Fg equals to mass times acceleration. Well, the acceleration we have is a centripetal acceleration AC. So basically, you have this. If you write the expression for the force, and then you write the expression for the acceleration, you have this simply this relation between each other. Okay. So okay, so this m here should be, let's say it's m2 here. Okay, it's the mass of the Earth, the moon. Okay, so the mass of the Earth times the mass of the moon times g over r squared equal to mass of the moon times v squared over r. So as far as the moon is rotating with this velocity here, instead of being pulled directly to the Earth, it's gonna stay on its orbit. Okay, it's gonna stay on the orbit doing a rotation. So again, see, this is a very important piece of physics, right? If we don't have this, the moon would go directly to the Earth. It wouldn't collapse, right? Based naively, you think that because there's only one force on the moon, right? But because there's a velocity kind of perpendicular to the direction of force, instead of falling to the Earth, the moon rotate around the Earth. Does that make sense to you guys? Any questions? Yeah, give me a sum up if you feel like it's good. Okay, good. Okay, so, and this piece of physics is everywhere. So you probably know already, right? In the solar system, we have a sun, and then we have a bunch of planets rotating around the sun. Okay, in that case, the orbit is actually not circular but elliptical. But that is a minor issue. Okay, actually, the main issue here is this. For example, if this is the Earth, okay, you consider the sun and the Earth, there's only one force on the Earth from the sun, which is the gravitational attraction, right? So how come the Earth does not collapse to the sun? Same physics, okay? It is because there's a velocity here. So instead of falling to the sun, this force provide a centripetal acceleration so that the Earth rotate around the sun. Okay, as I said, it's a little more complicated story because it's not a circular orbit; it's a elliptical orbit. But the idea is very similar. So exactly because the velocity here, those planets do not fall to the sun but rotate around the sun. Okay, you may say, how come it's so precise? How come the speed of the moon is that exactly right so that it can rotate around the Earth instead of falling? Why? Where does this speed come from? Okay, now you could answer this question from totally opposite direction. You could say, okay, there might be a lot of things at the very beginning around the Earth. Okay, they may or may not have this appropriate speed. So a lot of them may already collapse to the Earth, okay, in very long time ago, you know. Well, it's just so happened that the moon is the only object that has this property of velocity, so it can go around the Earth properly and with really stable orbits. Okay, same thing for the sun. There might be millions of things around the sun. A lot of them may not have this velocity, so a lot of them already being absorbed to the sun, collapsed to the sun, you know. And then what is left is this 8 planets. Okay, now you may know like Pluto used to be a planet. Now they say it's not. It's qualified because there's a hundreds or thousands of objects that's kind of very similar with very similar size to Pluto or even larger. All of them are rotating around the sun. So they are too small. So we don't consider them as planets. But we consider them as, but they're still rotating around the sun. So there's tons of things rotating around the sun. And it just so happened that these things left are the things that have the proper velocity so that they can rotate, okay? Now you may know that we live in a galaxy called a Milky Way galaxy, right? Milky Way galaxy. But do you know the galaxy itself is rotating? You may or may not. Do you guys know this? Give me some. Yes. So now you understand why it is rotating, right? Same thing. If it's not rotating, everything's gonna collapse because there's only, see this Milky Way galaxy like this, right? If it's 2 spiral or something like this. Well, there's only gravitational attraction. If it's not rotating, everything is gonna be absorbed together. So they're gonna collapse, okay, to the center. Well, exactly because of the rotation, the force does not pull this thing down, but the force provides the centripetal acceleration, so it's rotating instead of collapsing. Okay. Well, it turns out the universe is made of tons of galaxies. Okay. I think it's like either millions or billions. Okay, I don't remember, but there's all kinds of galaxies in the whole universe. But turns out that the whole universe is rotating as well. Okay. Well, again, same reason, right? If the universe is not rotating, it's gonna collapse because there's no other forces to balance gravity. So gravity is the only dominating force here. So everything's gonna collapse. So we won't have universe as we know it today. So see, this piece of physics is really, really important. You know, without this piece of physics, we won't survive. We won't exist. Nothing like Earth, human could exist because the whole universe will just collapse. Okay. So this rotation is, well, some of you may say that, or you may heard about this word called centrifugal force. They're saying that, okay, when you're rotating, there's a force, you produce a force called centrifugal force, and that centrifugal force balances the gravity, okay? I wouldn't want to do that. I wouldn't want to say this because this centrifugal force is not a real force, okay? It's a pseudo force, okay? So the real forces are the forces we talk about in this class, like gravity and normal force, tension, friction, et cetera, et cetera. But this centrifugal force is not a real force. It's an illusion, okay? Now, maybe when you're on the merry-go-round, right? You're going rotating and you feel like something's pushing you away and you feel like that's a force, you feel like that's or maybe when you're driving a car, right? Whenever the car make a turn, you feel like you're pushed away and you feel that's a force, but that's again, it's not really a real force, okay? The reason you feel like you're pushed away is this, okay? So when you're rotating, right? So your inertia wants you to go in a straight line, okay? This is Newton's first law. Without any force, you want to go in a straight line. But because you cannot go straight line, you're kind of forced to go rotation, either because of the merry-go-round or because the road you have is a turn or something. So you have to, you need a real force to provide you this centripetal actuation. So when you're pushed away to the wall of your car or to the seat, it basically the normal force provide you this centripetal actuation. So when you're in the middle of the car, when the car turns, right, you are actually not moving, but the car is turning. So you're kind of naturally go along. So then you hit the wall of the car. And then at that point, the wall provide you the centripetal acceleration. So you can go make a turn together with the car. So you have the centripetal acceleration. So when you do any problem in this chapter, always use the real forces. So always write the real forces on the right, on the left-hand side, and then write mass times centripetal acceleration on the right-hand side, okay? So do not consider anything like centrifugal force. They are not real, okay? Does that make sense to you guys? Yeah, I think this piece of physics is probably the most important thing we learn. I mean, in some sense, in this whole semester, because of the stability of this whole universe, right? Now, if you really think about nature, is really beautiful. See, those orbits that we move around the sun, it's been like that for not only years, but 10,000 years or even longer, like the Earth. Basically, whenever, since the Earth was born, you know, it's kept this orbit for very, very, very stable orbits for a really, really long time, okay? Well, this orbit gave us the right temperature on the Earth. We have the summer, we have the winter. It's exactly right. See, if you're closer to the sun, like in Mercury or Venus, right? I mean, nothing like this would exist. The temperature would be too big, you know, too hot, and then or too cold if it's away from sun. Well, if you're further away, right, then it's gonna be too cold, you know. So the Earth is exactly right in terms of getting the energy from the sun. So all life can exist on the Earth, and this stable orbit is critical for that, you know. It's a very simple piece of physics, but this piece of physics is critical, you know. Well, you may feel like this is not that hard, but think about it. People are trying to find out other like aliens, you know, civilization, or like in a different galaxies or the other part of the universe. So far, there's nothing, nothing we found out yet. So in some sense, we're really lucky, you know. Be a person, like a human being living, existing on the Earth is a very, very small probability event. It might be smaller than you get a lottery ticket, you know, you win lottery. It might be smaller, even smaller than that probability. So think about how lucky we are, you know, just by even living this. So, I mean, I guess we should really take our chance. I mean, pressure this, cherish this opportunity, and then live a good life, you know, because it's really, really rare event for us, okay? But I do believe there's some other kinds of life living in the whole universe, because obviously the universe is so big, you know. I mean, I don't believe we're the only people that's so lucky. There are definitely some other places, maybe a galaxy far away, you know, but we don't know yet. Anyway, so I mean, this kind of finished the full story I want to talk about the centripetal acceleration. Again, I really love the story, so read the notes again and make sure, I mean, watch the video, make sure you understand the story, okay? Now we're gonna go do some exercise. So basically we're talking about the, this section here, 7.4, that's the section that talks about, let's do some example in that section. Go to, that's 7.5, let's talk. So this is 7.4, okay? Okay, so yeah, this is the formula we talk about, okay? And so what do we want to talk about? Let's talk about, let's do this example here. Is that another very interesting example? And okay, yeah, 7.7 is good. Okay, so it's called buckle up for safety. Okay, so there's in this problem there's a car travel at a constant speed, 30 miles per hour. Okay, which is a 13.4 meter per second. Okay, on a level circular turn. Okay, so this is like something we encounter like on a daily basis, right? On the road, especially those country road, you have a lot of turns, and then, well, any part of the turn you can think about as a circular part. Okay, I mean part of the circle. So it tells you the radius of that circle, and then if you look from the top, this is what this look like. Okay, it asks you about what's the minimum coefficient of static friction allows the car to make a circular turn without sliding. Okay, so we're given basically this two pieces of information. Let's use this one directly, 13.4 meter per second, and the radius is a 50 meter. Okay, this is example 7.6. I would say turn on the road. So we have this part of the the turn, which is part of the circle. We know we're given the radius as 50 meter, and then we also know the speed of the car going into the circle. That's 13.4 meter per second. The question is, what is the minimum mu s we need? Okay. Well, if you look at this problem first, right, it sounds a little bit, it looks kind of a little bit crazy. How come this thing requires a minimum? What can we connect this, right, from these information to a minimum mu s? What does mu s have anything to do here, right? But you need to really think about the physics here, okay? So again, when the car is moving in like a turn, right, it's doing a part of circular motion. So as we know, the car need a centripetal acceleration, AC, point toward the center, right? That's what is needed. And we even know how to calculate it. It's basically V squared over R. So given what we have, we can calculate this AC. So, but what can provide this AC here, right? Remember, we have Newton's law, force equal to ma. So we need some real forces to provide you a centripetal acceleration. Okay, what can that force be, right? If you think about this car, right? Let me draw the car like from the front point of view or from the rear. See the car's going into the paper, right? And then we need a centripetal acceleration from here, right? We need some forces going along this direction, point toward the center, right? So what can that force be? Okay, I guess this is not. Well, we have normal force, gravity going along this direction, but it won't help. We might have some fraction going opposite direction or along this the direction of car's motion, but that's not help either, because we need a force to the side that provide us a centripetal acceleration, right? So what kind of force is that? Well, there's only one force that we can have, because there's in kind of a surface, it has to be a friction, okay? And it actually has to be a static friction, because there's no motion of the car going along this direction, right? It is static, there's no motion, so it's a static friction. So basically, that just tells you that you need so you need to have a sufficient large static friction to provide you the acceleration. Well, we know the maximum static friction is given by a formula like mu s times n, right? And so basically, it says basically, well, when you the case when you need only a minimum mu s is when the case that you actually use this maximum static friction. So to solve the problem, we need to assume that the force that providing you the acceleration is the static maximum static friction here. Okay. Now, according to Newton's second law, there's only one force going along this direction, which is just this static friction, and it reaches the maximum value. So according to the second law, we have F as maximum equals to MAC, right? That's our Newton's second law, force equal to mass times acceleration. Now, what about normal force? Okay, if you draw the free body diagram here, you see that normal force certainly just equals to gravity, okay? So you can plug in here. So you have mu s times mg for the maximum static friction, okay? That equal to mass times v squared over r, where this is your formula for centripetal acceleration, okay? Now, as you see here, mass cancels out. So mass is, it doesn't matter. So it doesn't matter how heavy the car is. It's the same behavior. So from there, you can solve for mu s, okay? So mu s equals to v squared over gr. So plugging numbers, v squared is 13.4. G is 9.8 meter per second square, and R is 50 meter, okay? So together we have this combination here. So now you go ahead and calculate it, calculate number. So you got 0.37, okay? And there's no unit for it. You can, as you can see here, meter square per second square divided by meter per second square and meter, and the unit simply cancels out. So what is left? Simply 0.37, and that is the mu s, the value for mu s. So that's the minimum mu s you need, okay? Now, certainly the larger mu s you have, the better, because then you may not need to reach this maximum static friction to balance, to provide this acceleration. Well, in this case, notice the acceleration is fixed, right? It's this much. So the larger mu s you have, when mu s is larger, you have this side larger, but in that case, you do not need to use the maximum static friction. You can use something a little bit smaller. That's certainly fine. So the larger mu s you have, the better, okay? Well, when you drive your car and make these turns, what do you feel like is something, you may not feel like how much mu s you need, but you have a feeling that when you're driving the car a little bit too fast, it's kind of harder to make a turn, right? You agree? Well, when you slow down, it's easier. Well, again, that's the same thing here. Look at this, right? In reality, this mu s is kind of fixed. It's already given. So, well, the larger v you have, the bigger static friction you need to provide you the acceleration to go. Well, that you feel like it's harder to make the turn. Well, the smaller v you have, the smaller f you need. Well, you may not need the whole mu s to provide you the maximum static friction. You may only need a part of the maximum static friction, but basically you're safer. So, but if your v is really large, it's so large that even the maximum static friction is not enough to provide you this. What's going to happen? So what's going to happen is you cannot, because there's no enough force to provide you the acceleration, the velocity change, the direction change is not sufficient to follow the circle. What's going to happen is you're going to go run out of the circle. I mean, basically you run out of the road. So it's going to be an accident, right? So I would say when you drive, I mean, I have to, let me say this, okay? I'm not sometimes I go a little bit higher than speed limit when I drive on a straight highway, you know, because I'm a little bit, I want to go somewhere faster or something. But whenever there's a turn, it tells me the speed limit is 30 miles per hour or something. I normally follow that speed limit, okay, whenever they make turns. I know normally they wouldn't just put a speed limit so that you can barely make it, right? That'd be too dangerous. So normally they will put a speed limit sign that's kind of give you some, there's a little bit of a window of safety so that you even if you drive that full speed limit at the speed limit, you're still okay. But I don't recommend you guys to go above the speed limit because you need to provide some window of safety for yourself, you know. You should really follow the speed limit, okay, whenever it has turns, because the consequence will be really severe. You may just go off the road, you know. That's really dangerous, especially when you go to somewhere you have never been there, you know. It's a new road, and there are a lot of signs like when you have turn like 30 miles per hour, 20 miles per hour, just follow it, you know. If you took a little bit longer, but it's way safer, okay. Another thing you need to keep in mind is when it's raining or when it's snow on the road, that reduces the coefficient of friction. So you have a smaller coefficient, okay? That means the friction, maximum static friction you can have is going to be smaller. So it'll be harder to make a turn on those sleepy roads. So in those cases, you may even need to reduce your speed further, okay? Whenever feel like you need to have a speed that whenever you make turns, you feel comfortable that you can control the car well, and the car can rotate. I mean, it can go along the road pretty well, okay? So again, this is another piece of physics I think is really useful for us, okay? Now you know we need to follow speed limit, you know. There's some reasons for that, you know, because this piece of physics, because you need a friction, static friction to provide you the centripetal acceleration whenever you make a turn or follow this curved road, you know, on wherever you go. Okay. Any questions? We're good? Okay. So let's see, what else do I want to say? Okay, so this pretty much finished the bulk part of this about this physics of centripetal acceleration. As I said, this part is the more important part in this chapter, because for the kinematics part, we kind of already seen it before, in chapter 2. It's very similar to chapter 2, but this part is kind of new for us. Well, it's in some sense the application of chapter 4, Newton's law, but you have a new acceleration to consider, which is centripetal acceleration. And in this case, it's kind of like we know the acceleration already. At least we know the formula here. And then what we need is find the forces or set up the forces to provide us this acceleration, okay? If we fail to do that, we cannot have a rotation. So this kind of new thing for this chapter. Well, the problem we solve in this chapter, I mean, for dynamics part, we kind of still do like a free body diagram and set up equations, but we normally only cares about the direction, one direction of the motion. We care about direction where we have this centripetal acceleration. We do not care about the other direction. Okay. So another interesting case that we can talk about for this piece of physics we learned is about roller coaster. Okay. I know. I bet you guys, all of you guys, have been on one kind or the other kind of roller coasters before in your lifetime. So because it's so popular, and sometimes you go upside down on your roller coaster, right? Now you may feel really scared because it's upside down, right? You may feel I may fall off. Now you learn you do not. Okay, it's not only because you have the safety belt, I mean, or whatever safety device they put there, but also because of physics. You simply won't fall down as far as you have enough sufficient speed. Okay, it's the same thing as the motorcycle in a cage, right? So today let's do two part of it. Okay. So let's imagine there's a roller coaster car on the track, and it's kind of going along this two. Well, it's kind of impossible to do like this, right? Let me maybe sorry. What I meant is okay. Wait, you have to go like this, right? But then let me draw a little bit different. So maybe and then it goes like this, and then this. Okay, that's possible then, right? Okay. All right. Not very well drawing here. Okay. So anyway, let's consider these two positions, A and B. Okay. Let's say the mass of the car is just let's say it's 800 kilogram. The mass and the whatever people you have on the car together has 800 kilogram. And then let's also say the velocity we have here is the speed. Okay, it's moving constant speed. Let's say 20 meter per second. That's pretty fast. I mean, let's just, for the sake of the problem, let's do it 20 meter per second. Okay, let's say the radius. Okay, so both part of this is part of the circle. Let's say the radius here you have is 20 meter. That's a really large roller coaster. Radius 20 meter. The diameter is 40 meter. Wow, that's big. So, and my question here is for you is calculate the maybe let's put it this as well. Okay, calculate the normal force on the car. Normal force on the car in these three positions, in A, B, and C. Okay, A and B and C. Okay, 3 positions. Okay. Now, again, these are Newton's law problem, but remember, we only care about this direction, okay, the direction that's when you have centrifugal actuation. Let me give you some tips. So when it's on the top, the centrifugal actuation going down, okay? When it's at the bottom, the centrifugal actuation going up. When it's at the side, the centrifugal actuation going toward the center, right? So each case is always pointing toward the center, okay? So what do you need to do here is do free body diagram for the object and figure out which direction, what force do you have and which direction they go. And again, the total force is needed to provide you the centripetal acceleration of the object, okay? And from there, you can set up your Newton's law, right? F equal to ma. Well, A here is just the centripetal acceleration you have, okay? So go ahead and do that, okay? Send me your answer after you finish each part of it. Okay, maybe let's talk about this together. We're about 10 minutes. I think it's should be have sufficient time to do it. So I think this problem is a good problem because it's I see if you after you understand it, you feel like it's really interesting. It's very simple settings, but very interesting physics. So let's start from the first case, right? So this is upside down here, right? So you have gravity going down, and then you could have a normal force going down as well. So you have two forces going down, okay? And you have direction acceleration going down as well. In solving this kind of problem, I normally set up the positive direction of the coordinate system goes same as the direction of acceleration. That makes things easier for me because I always put positive numbers for acceleration. So if I do this, you have total force equals to mass times acceleration. So you have, in this case, mg plus n, because they're both going positive direction, okay, equals to mac. That's your equation. So it kind of helpful if you can solve for AC first, you know, is equal to v squared over r, where v is 20 meter per second, square that and divided by 20 meter. So that gives you just 20 meter per second squared. So look, this is a huge acceleration, right? Because our free fall acceleration is only 9.8. So this is really huge. So you definitely feel something when you ride this roller coaster. So okay, now for this, for the first part, right? Mg plus n equal to mac. That means n equals to mac minus mg. Okay, so you can factorize mass is ac minus g. So you basically have 800 kilometer times 20 meter per second square minus 9.8 meter per second square. Okay. So if you do this calculation, you get 8160 Newton. Okay. It's about 8,000. Okay. That's the answer for A. Now let's look at B. Okay. What's the difference? Okay. In the case of B, the gravity certainly still goes down. However, normal force goes up now. And because the surface is underneath the car, okay? And then also the acceleration now goes up because the point was center. So if you set up this as your positive direction, you have for the second case, n minus mg equals to mac. So n equals to mg plus mac, okay? So you factor out this, you have 9.8 meter per second square plus 20 meter per second square. Okay, m is 800. So together you got 23840 Newton. Okay, that's the B. Okay, now what about C? On C, right? This is on the sideways. So the direction of acceleration is going toward the center like this. Well, the normal force, because the surface is here, so normal force goes like this. Gravity is going down still, but that is irrelevant for us because we're only interested in the direction of the centripetal acceleration. Gravity is going along the perpendicular direction, so it won't enter the problem. So in the third case, you simply have n equals to mac because that's the total force going along this direction. That's mass times centripetal acceleration. So in that case, you simply have 800 kilogram times 20 meter per second squared. So in the last one, you got 16,000 Newton. So you see these three different cases, right? You got three different answers. Why is that? essentially this case, the second case is the largest, you have largest normal force because the gravity is going down. So in order to provide the same acceleration, you need to have bigger force to balance the gravity and provide the acceleration at the same time. So it's larger. See, it's like these two terms combined. Okay. Well, in the first case, you need the smallest normal force because gravity in this case help you. So both these two forces provide the acceleration together. So n itself only is part of this MAC here. So that's why it's smallest. Well, in the third case, it's kind of in the middle because gravity has no contribution. The only one you can rely on, count on, is normal force. So that's give you some number in the middle. Okay. Does that make sense to you guys? Again, I think this problem is really good because, see, the setting is really not that difficult, and it's essentially one-dimensional problem. But depending on the position of the object, you could have all different kind of results. You know, it's all different. You know, and actually, there's one case we didn't talk about, which is this case. You may want to think about it as well. I mean, try to calculate it by yourself. So if the object is here, right? Well, it's still moving with same speed as 20 meters per second. Well, in this case, you get a different number again, because in this case, gravity is going down, normal force going up, but acceleration is going down. So you actually have a mg minus n equals to mac. So it's again going to give you a different result for n. So the problem is setting simple, but the physics is abandoned. You know, there's all kind of interesting cases you can talk about. So try to study this problem. It's a very good problem. It tells you a lot of, see, all these feature about centripetal acceleration. And as you see here, right, the acceleration itself may change directions, right? Going down, going up, or going to the left, you know, it's all different. While the force may change direction, like normal force, right? Depending on where the surface is. So it's all good, okay? It's the various different physics you can think about, okay? Do we have any questions about this one? We're good. I think now you're good to solve all problems in this chapter for chapter 7, you know, and supposing you should finish before the end of this week. I'm going to double check about chapter 8 problems and make sure that's going to be the things we cover, and probably I'll set up to be like a due date to be like a Tuesday or something, Tuesday night or something, so that you guys have sufficient time to, I mean, you can finish before you take the final, you know, on Thursday. So, and we can even talk a little bit about if you have any questions about the homework or anything. So, I think that's all I want to talk about today. Tomorrow we'll finish the last part of this chapter. I'll talk a little bit about astronomy, which I think mostly, I mean, it's related to this part of physics, but also it's kind of interesting to know by itself, because we live in this universe, right, for about 100 years, which is nothing compared with the age of the universe, but it's still quite a bit for us. And we have every day, we have a lot of days and everything. So yeah, it's worth to know a little bit the universe, okay? Anyway, so that's all I want to talk about today.